Welcome back, everyone. In this question, brought to you by popular demand, this is 1 a day 9 from 365. This is question number 2. And the question asks, it is found experimentally that a 6-pound weight stretches a spring 6 inches if the weight is pulled 4 inches from the equilibrium position and given a downward velocity of 2 feet per second before being released. Set up the differential equation associated with conditions described in motion. Use units of feet and remember the mass in weight divided by the force of gravity, appropriate units. Find the position of the weight as a function of time. Find the amplitude, period, frequency, and phase angle of the motion. Okay, so our initial situation is here's the unstretched spring. And when we apply that 6-pound weight, we find that it displaces the spring from its natural position down 6 inches. And that's really helpful because that allows us then to find the spring constant. So in this situation, initially, we know that mg is equal to kx, the displacement, and mg is the 6 pounds of the weight, and x is the displacement in feet. So we have to convert 6 inches into feet. So to find k, we simply can plug in, and we get k is equal to mg over x. And if you plug in mg, that's 6 divided by 12 gives us that, or sorry, divided by half gives us that the k is equal to 12 pounds per foot. And that is the correct units that we're expecting. Again, x is the 1/2 feet here, and mg is the 6 pounds. Okay, so now we have our k, which is some of the information that we needed. And now we're going to go ahead and set up the differential equation. We know from Newton's second law that we can write this differential equation as 0 is equal to the second derivative with respect to time. This is the acceleration plus omega squared x, where x is the displacement, and omega squared is equal to the square of omega squared is k over m, where k is the spring constant we just found, and m is the mass of this weight. So in order to find m, we would need to divide both sides by g. So this is 6 over g, 6 pounds over g, which is for us, we're going to take as 32 feet per second squared. So that reduces to 3 over 16 pounds per second squared. Okay. And let's see, we can plug this into here. And so K was 12 pound per foot. And then if I invert and multiply, this is going to be 16 over 3. This is going to be feet per second squared over pound. And so 3 goes into 4. So this is 4 times 16, which gives me 64. Let's see, the feets cancel, the pounds cancel, and so you're left with 64 over 1 over 6 squared, which is exactly right, because omega is the square root of omega squared, or omega is the frequency that we're asked to find. And so we know omega, and so we already found frequency in part C. Square root of this is, okay, so the differential equation then is 0 equals, and so homogeneous plus 64x. Since this is a homogeneous equation, I'm going to let x equal e to the rt, which gives us the characteristic equation r squared plus 64 equals 0. Solving for r, we're going to get r is equal to plus or minus 8i, which means our characteristic or homogeneous equation, x of t, is going to equal c1 cosine 8t plus c2 sine of 8t. All right, and so that's really helpful. Now we have the equation of motion. Let's see, what else do we need to do? We need to apply the initial conditions, which we didn't talk about. So going back to the problem, initially it said uh, if the weight is pulled down 4 inches, so we know that x at time t equals 0. Wonder condition, right? At t equals 0, our initial condition is 4 inches, which is the same thing as 4 over 12 feet, which gives us 1/3 feet. Okay, so that's our initial condition for position. And for the velocity, it said that at time t equals 0, it was given a downward velocity of 2 feet per second. And in our notation here, we set up our coordinate system so that generally it's accepted as long as you're consistent, that if we go down, that's positive, and if we go up, that's negative. And so our velocity here will be a positive because it's in the downward position. Okay, so it's going to start 4 inches below, and then it's going to be pushed down, so it's going to go down and then come back up is the motion that we're anticipating from that. And so we can use this equation to determine constants. So x of 0, plugging in the initial condition there, is equal to 1/3. And the sine of 0 is 0, so this just leaves 8 times 0, which is cosine of 1. Our cosine of 0 is 1, so that gives us then immediately what C1 is. C1 is equal to 1/3. If we take the derivative of x of t, we get negative C1 sine of 8t times 8 plus C2 cosine of 8t times 8. Okay, and then evaluating this at t equals 0, the sign is going to drop out, and we're just left with, of course, cosine of 0. That's going to give us 1, and so we have C2 times 8 equals, well, what was the initial velocity? It was 2. So this is going to give us 2 times 8, C2. So C2 is going to give us 1/4. All right, now that we have C1 and C2, our equation of motion then, maybe x of t equals, was it 1/3? 1/3 cosine of 8t. The reflection on the light is kind of hard to see the writing, so if you wonder why I'm pausing. And then we have 1/4 sine of 8t. Okay. So that's one version. And now we can also convert this using the single expression for the sine and cosine, expressing it as a single function of sine. And that's of the form x of t, sometimes called a for the amplitude, times sine of, I think they use omega t, yeah, plus a phase shift phi. So a is the sum of the square roots of these, so it's going to be 1/3 squared plus 1/4 squared, and that's going to give us well, it's going to be 16 plus 9 over 3 squared times 4 squared. 16 plus 9 is 25. Square root of 25 is 5. This is going to be square root of 3 times square root of 4 squared, so that's going to give me 3 times 4. So this is going to give me then the amplitude is 5/12. All right, so we got the first part, 5/12, and this is part C. That's the amplitude, and we're going to have sine. We already found the frequency, that's omega. So the period is 2 pi over omega, which is 2 pi over 8? So pi over 4. Pi over 4 is the period, and now we need to find the phase shift. So phi, the tangent of phi, is equal to C1 over C2. C1 over C2. So C1 is 1/3. So this is going to give us that phi is equal to the arctan of 1/3 times 4/1. The reciprocal of C2 is flipping it over, so it's 4/1. So that's the tan inverse of 4/3. And that gives us, which gives us 0.927 radians if you plug it in. And since both the C1 and C2 are positive, we know this lies in quadrant 1, and this lies in quadrant 1 as well. So finally, then we have that this is plus 0.927 radians. And so there is our equation of motion. This is our phase shift. This is the frequency. This is the amplitude. The period is pi/4. And was there anything else? I think that it was all the questions answered. Okay, I hope that was helpful. And I'll see you in the next video. We're going to continue on the same, since we're going to use a lot of the same information. So this is one a day 9 again. This is problem number 3. And so number 3 says, now assume that a damping force given in pounds numerically by 1.5, the initial velocity or the instantaneous velocity in feet per second acts on the above weight. Okay, so everything that we have just done for the ideas of omega squared, and all that are still the same. The only thing that we've changed now is that this is maybe in some sort of medium where there's a damping force that is equal to 1.5 times the initial force. So that changes the form of the differential equation. And so we'll kind of step back a second just to kind of show where that comes from, and then proceed with the solution to this problem. So setting this differential equation up. Daddy. All right. So now that we know that the initial velocity has a force that is opposing it, a damping force, we can write the differential equation. We know omega squared is still equal to 64 as before. And so this differential equation is going to be the second derivative with respect to time of the position function plus 1.5 times the dampening force, and then plus 64 times x, and that's going to equal 0. So this is the differential equation then that we would try to solve. Since it is a homogeneous equation, we can utilize the fact that we know that with constant coefficients, we can use something of the form x of t is equal to e to the rt. And if we plug in that, we get the characteristic equation r squared plus 1.5 r plus 64 equals 0. If we solve this characteristic equation, we get r is equal to, I use the quadratic formula, so it's negative 1.5. I change 1.5 to 3/2, just because it's easier to write out. So this is negative 3 plus or minus the square root of 10/15 as a result of simplifying inside I, all divided by 4. This is the square root of 10/15 since the 64, the 4ac is larger than the 3/2 squared. And then pulling out the common denominator. Okay, so that's where that comes from. And so this allows us then to write the solution for this particular one, recognizing that we're going to have a real and an imaginary part. So the real part is going to be the negative 3/4 t with the exponential. So that's going to be the dampening piece. And then this part, the imaginary part, is going to be the oscillatory part of the motion. And so we're going to get x of t is equal to e to the negative 3t/4 times c1 cosine the square root of 10/15/4 t plus c2 sine square root of 10/15/4 t. Okay. All right, and if we keep everything else the same as in the previous problem, then we still also have that x of, or sorry, well, I guess I should, x prime, the initial velocity was 2, and the x position was a half foot. No, it was the third. I think it was the third of a foot. Yeah, it was the third of a foot below because it was 4 inches, so it's a third of a foot low. So we have these still initial conditions, and so we would still use these to find the constant C1 and C2. So the first one, if we plug in 0 everywhere, this is going to give me 1. This term will give me 0. Cosine will be 1. So you're going to get C1 is actually 1/3. So that one's really easy to find. Taking the derivative and plugging in what you know for C1 in that regard, or in that case, and simplifying, you get that B was equal to 9 over, so not B, sorry, C2. So C1 is 1/3 and C2 is 9 over the square root of 10, 15. So those are the two constants of integration, or two constants that come out of that from the constant of integration. And so these are the specific ones. So the equation of motion in its entirety would be e to the negative 3 t over 4, 1/3 cosine 10, 15 square root of that over 4t plus 9 over square root of 10, 15 times the sine of 10, 15 over 4 times t would be the total equation of motion. Okay. All right. I hope that was helpful, and I will see you in the next video.